So this final video for Lecture 7 looks at the stress-strain PowerPoint. Begins on slide 19 and is looking at Poisson's ratio. Rather amusingly, I thought, but then I've got a weird sense of humour. I've put a picture of a fish being squeezed. Fish, Poisson, French. But the idea of the squeezing is important here, as you'll get from the next slide, from slide 20. You've got a definition there that Poisson's ratio is the proportional decrease in one direction of material to the stretch in the other. So it's like, if you imagine pulling blue tack, the longer it gets, the thinner it gets. And the ratio, Poisson's ratio, describes that. So very briefly, Poisson's ratio is the change in one direction over the original length divided by the change in the other direction over the original length, and it's a negative value. So as one, as you can see in the diagram, if you've got the PowerPoint in front of you, as I squeeze here, it's going to get thinner, but it's also going to get taller. Okay, so I could be applying the force to the squeeze to make it shoot up, or I could be pulling it and thinning it out. It doesn't matter which way around you think about it, the ratio idea holds the same. That really is Poisson's ratio in a nutshell, but there are a couple of examples that are looking at that. First one starts on slide 21. It's looking at a steel wire. Hooray! Another one. Steel wire, length 3 metres, diameter 1.5 mil, used to support 150 kilos. And you're looking at calculating the extension of the wire and its changing thickness under tension. So you're going to have to use previous information, previous equations from stress strain, and you're going to have to use your Poisson's ratio. If you pause the video and then come back to it, I'll show you how you go through it. So you should have had a go at the question about the steel wire of length 3 metres that's being stretched, and you've been asked for the extension of the wire and its thickness when it's under tension. So obviously, you know, if it's being stretched, it's going to be thinner. So that's your Poisson ratio. How much is it being stretched? Well, that's using your Young's modulus from the previous video that we talked through. So we know that Young's modulus is force over area over delta L or delta X over X. So delta X equals Fx over EA. F is going to be mg. E, we're given. Area is going to be pi. We'll call it d squared over 4 because that's what the notes have done, but that's the same as r squared over 2. Substituting in the numbers we know, we can bring that 4 up to the top as well. So we can say 4 by 150. So this 4 here is the 4 from... Sorry, this 4 here is this 4 here. We've just moved it up. By 9.81 by 3 metres. And we're going to divide that by pi by 1.5 times 10 to the minus 3 squared, and by 210 times 10 to the 9. So that will give us an extension of 11.9 millimetres, so quite significant. We can then transfer that into our Poisson's ratio. So we know that our ratio, which is the letter V, is going to be change in diameter over original diameter divided by change in length over original length. We can rearrange that to say change in diameter is d naught Poisson's ratio delta L over L naught. Substituting our values, we're going to have 1.5 times 10 to the minus 3 times 0.3 times 11.9 times 10 to the minus 3 divided by the original 3 metres, which equals 1.79 times 10 to the minus 6 litres. That's 1.79. So that's a very simplistic use of Poisson's ratio. It's literally just an equation that you're going to substitute some numbers into to work out the ratio of how much something is stretched and it's also compressed, or vice versa. There is a more complex question to have a go at, talking about a block of material used to support a piece of equipment. Beginning on slide 23, if you have pause and have a go at that, and then I'll talk you through the solution. So you should have had a go at the question about a block of material being used to support a piece of equipment to reduce its vibration. If we draw a picture, I know there's a picture there, but if we draw a picture of what we're looking at, we've got our equipment and we've got our vibrational pad, and it's in a housing, and we want to know, we're being asked the maximum load before the material touches the sides, so before the material stretches that way, till it touches the sides. So the delta x, the change in dimensions, is going to be the size of the hole, which is 100 mil per side, minus the size of the leg, the size of the support, which is 90 mil in 90 mil per side. So we're looking for a 10 millimeter change. That's going to mean a strain of change in length over original length. So 10 over 90, we're going to have a strain of 0.1 recurring. So in the x direction, the direction the green arrows are showing, there's going to be a strain of 0.1 recurring. Poisson's ratio is going to be, that's our transverse strain, or T strain. Poisson's ratio is our transverse strain, delta x over x, divided by our axial strain, or delta y over y in this case, or the change in the red arrows. We don't know that, but we do know the Poisson's ratio for the two materials being considered. So if we think about, we can rearrange that as axial strain equals T strain over Poisson's ratio. So if I jump to a new slide for rubber, that's going to equal the axial strain is going to equal our transverse strain, our maximum transverse strain before it touches the side, 0.1 recurring, over the Poisson's ratio for rubber, 0.5, which is 0.2 recurring. And similarly for cork, the axial strain is going to equal 0.111, so the maximum transverse strain we can have over 0, which is going to give you an infinite axial strain. So the cork, it doesn't matter how much you push on the top, it's never going to touch the sides. Okay, it's going to break eventually, but it's never going to be limited by its axial strain. So what we're saying here is, no matter how big the force where the red arrows are is applied, it will never touch the side of the hole it's sat in. The green arrows will never expand that far. However, with rubber there will be a limit, so we can still work and take the rubber bit a little further. So this is now only working with rubber, because we've said the cork will not stretch. We know Young's modulus is stress over strain. So we know that stress is going to be Young's modulus times strain. Young's modulus for rubber is 15.4 times 10 to the 6. Our strain that we've worked out is 0.2 recurring. So our stress is going to be 3.42 megapascals. Stress is force over area. So force is stress times area, which is going to be 3.42 megapascals, or 10 to the 6, times 0.1 squared, which was your area of your contact. And that equals 34.2 kilonewtons. And finally, to get a mass, well, weight is mass times gravity, so mass is weight over gravity. Your maximum weight, 34.2 times 10 to the 3 over 9.81, 3.49 times 10 to the 3 kilos. That is the maximum mass before the before the rubber pad will squash out and fill the hole that it's sat in. And that concludes the question. There are a couple of other extra little bits just at the end of the Poisson ratio section. If the equipment is vibrating, then the forces on the pad will be variable through the vibration cycle. So you're going to be thinking about the average load being equal to the static load. So the frequency and the amplitude of vibration affect the maximum force and the forces on the pad. And can be much higher than the static loading that we've just talked about. And there is an equation that relates them on slide 26 of the PowerPoint. On slide 27, the final bit, there is a YouTube link. It's not compulsory viewing, but there is a few examples of materials that do not follow Poisson's ratio. So when you stretch them in one dimension, you stretch them in all the dimensions. So the weird things, I forget the actual name of them, they're not needed for your course, it was just for interest. But the best example I can think of is it's like a little toy ball that you can get as a child, made of lots of plastic links, and when you throw it in the air, all the links get bigger together and they all move out together, and then when you catch it again it's back small again. So there are materials which start off very small, and then as you apply a force they get bigger in all directions equally and don't follow Poisson's ratio. They've got a special name. There's a link at on slide 27 that will take you to a short YouTube clip showing you some of those and the molecular levels of some of those. But that concludes the Lecture 7 video on Poisson's ratio.